gate capacitance and saturation?
Is it 2/3 C-ox times WL?
Yeah, it's 2/3 C-ox W over L. That came from, let's just go back here. Where are we? Yeah, that's this part right here, right? So that's kind of my average, but we're going to use, like, we're just going to ignore that 2/3. Just to simplify things, we're just going to use C-ox W over L. So you could have said either one, but that's fine. Justin, you got 2 points. Okay, now I have a bonus question for everybody. And we need to draw a picture. Okay, I need to explain a few things here. An inverter, like so. And this inverter, it has an N channel down here, and the size of this N channel is 300 nanometers by 30 nanometers. So that's the width, that's the length. And this PMOS, we like to normally make it bigger just because it has a lower mobility. So it's 900 nanometers. Nanometer is 10 to the minus 9, right? By 30 nanometers. And we are told that C-ox for this process, it's the capacitance per unit area, is 25 femto farads, right? What's femto? Our little friend, what's femto?
10 to the negative 15.
Right. 25 femtofarads per, and it's per unit area, so it's per micrometer squared. By the way, these are practical values that you would have in a real process, okay? And I'm looking in here, and I want to know what's the capacitance, Cn, okay? I'm going to call it, looking into the gate, Cn equals question mark. Now I have to tell you two things to help you out with this. First off, whether you're, remember we're only interested in saturation and cutoff in digital circuits, and in both cases, for a transistor, let's just go back to our little picture here. If you're in cutoff, the input capacitance is C-ox W over L, and for saturation, we're going to use the same thing. C-ox is W over L, okay? Or C-ox times W times L. So we're going to forget that 2/3. We're going to use the same equation for both of them. And then the other thing to note is that when you look at capacitance, it's kind of like an AC characteristic, right? So the thing is charging up and down. And you may remember from your what's electronics 12507? I don't know. But let's say you had when you did your like common source amplifier. No, you probably did it with a BJT. I don't know. I'll draw it like that. Remember? Or let's do it with a MOSFET. And when you did the AC analysis of this little circuit, right? So that was an AC input. I don't know if you remember this, but this power supply, you treated that like a ground. You remember that? It was an AC ground because an AC power supply voltages look like 0 and currents look like an open circuit, right? So you did that. So similarly, when we're looking at the AC capacitance, looking into this, we can treat this like a ground, an AC ground, okay? So that kind of helps you. Okay, so that's the question. What's this input capacitance going to be given these size of these transistors and this capacitance per unit area? So we'll understand what a typical value is. So let's go to our course web page here for a sec. Bonus quiz.
Professor.
Yep.
So we only need to determine the cutoff and cutoff / saturation, correct?
Yeah, we're assuming that we're in cutoff or saturation. Bright space yet? I haven't. Well, you could. You can put whatever voltage you want here on this input to this inverter, but I'm just saying that our assumption is that these devices are in cutoff or saturation, and since they have the same input capacitance in both situations, it doesn't matter.
Oh, okay. Thank you.
Okay. You got a little less than a minute. Assignments. No idea. Hopefully, when the TAs mark it, it'll show. They'll take the most recent one, as long as both of them are submitted.
Okay.
Oh. Oh. I don't know. 9. Couple more minutes.
That in exams, you can mark the questions you want to go back. In price
Mhm.
place, you can't.
Lagging. It's all run. Okay, 8:59. We're gonna go through the answer. So what's the capacitance? Normally the capacitance we're told is C aux times W times L, right? And in this case, we have two capacitance. We're gonna be seeing a capacitor here, gate capacitance, which is going to go to ground. And we're going to see a capacitance here, which is going to go to ground. And depending on what the voltages are, either in saturation or cutoff, but it's the same input capacitance. So that C aux is going to be the same, and the equation is going to be the same. So we can break this out to be like C aux times sort of like W1 L. Well, say I called that like Q1, and that was Q2. W1 L1 plus C aux W2 L2, or I can just say C aux. The L1 and L2, they're both the same here, right? The only thing that's different is just W1 plus W2 times L2, which equals C aux, which we're told is 25 femtofarads per micron squared. And W1 plus W2 is 900 nanometers plus 300 nanometers, but I'm going to put those in micrometers because I want to multiply by micrometers. So a nanometer is like 1,000th of a micrometer. So this would be like 0.9 plus 0.3. So I could say 1.2 micrometers, right? It's messing up. Times L, which would be 0.03. This 30 nanometers over here would be 0.03 micrometers. And if I multiply that all out, I will get 0.9 femto, my little friend, femtofarads. Or you could boy, this is really messing up. I don't know why. You could also say 900 attofarads, right? So in chips, when we're talking about capacitance, they're in like femto or even attofarads. Like a smaller transistor here, transistors would be like, 100 attofarads. So the capacitance on our chip are really, really small. Like this is like 10 to the minus 18 farads, right? And so that means we don't use a lot of power and we can go really high speed because there's really, really small capacitance inside the chip. Any questions about that? 0.9 femtofarads, yes, Harsh, you got it right. Part marks? No. That's times, but if you don't believe in God, then there's the God of quantum physics, which is Heisenberg. I told that to my kids one day and they laughed. They said, "Oh, Heisenberg, no, that's the guy that kills everybody in Breaking Bad." Anyway, don't trust your calculator. Always do the calculations in your head. Do some estimation all the time. You should be doing it all the time. Why would you leave it to femto and not convert to units? Well, you could leave this as 9 times 10 to the minus 16, right? If you want to. Ooh, let's go. Oh no, we're going to go here. We're going to go to the next set of notes. Okay, so